Hello, Algebra 1 superstars, and welcome to Lesson 1.08, which is an introduction to linear inequalities. Now, the last time you guys were introduced to inequalities was actually 7th grade. You don't do them at all in 8th grade, and maybe your 8th grade teachers did a lot of review in 8th grade, but I doubt it. So a lot of this is going to feel like it's new for you. Some of it will be you trying to remember what the heck happened in 7th grade, and I'll do my best to get you through it all. So let's start. This is our second goal, and that is I can solve linear inequalities. That's going to be lesson 1.08 and 1.09. Today is going to be a lot of background on inequalities, and then 1.09 is going to be more of the focus on solving. In fact, we're not going to solve too many inequalities today at all. But I keep saying that word inequality. Let's go ahead and make sure we understand the difference between an inequality versus an equality. There's actually 4 different signs you need to know for inequalities, and there's only one sign you need to know for an equality. Right? In equality, you have the left side of an equation, you have the right side, and what connects those? Well, an equal sign. Equality equals sign. But an inequality also has a left and a right side, but then it has 4 different signs that can separate the left and the right side. Now, I'm not going to tell you what they are, but I am going to draw them out for you, and then I bet you'll recognize them. Okay, so the 4 signs that we have are this guy, this one, and this one. Now, you've seen those before, and you're probably looking at those, and you're like, oh, those are the alligator mouths. You're right. There are, however, particular names for these, and you do need to know their names. If you don't know their names, the alligator mouth trick isn't going to be enough to get you through today. So here is how I remember them. I start with the word less than, because one of these symbols is the symbol for less than. And I look at the L that's in less than. And if you turn that L just a little bit to the right, and you write it again, you can see that the L matches this symbol right here. That symbol's like an L, a slightly crooked L. That is the less than symbol. And less than means smaller than. Okay, if we look at our next symbol, that is, of course, greater than. Greater means more. And then we come to these last two, which is a less than and then a greater than symbol with the line underneath. These symbols are actually a shortcut way to write 2 symbols at the same time. In fact, this symbol down here is actually this symbol, and then there's an or in between, and then this symbol. So this is actually a less than symbol and an equal sign put together. And we read this as less than or equal to. And the last one, of course, is greater than or equal to. And we'll see how those are used actually pretty darn soon. So I have 2 examples for you guys to really understand what inequalities are and how they're used and how they're different than equalities. So if you have enough time, you should certainly pause this video and try and go through and solve these. But if you're not sure you'll have enough time, you can just let the video play and just listen to my nice soothing voice while, of course, taking notes. So the first question says, what does it mean to solve an equation? Well, to solve an equation, right, you have numbers that are happening to x. And when you solve an equation, that means you isolate, and I'm going to say, and find the value of x. So an example might be you find something like x equals 5. Now, what does x equals 5 actually do? Well, that's when you substitute it back into the original equation, and it causes the left side of the equal sign to equal the right. So the whole point of a solution is when you substitute it in, it makes the left equal the right. Okay, so let's try one. How many solutions does 2x minus 5 equal 3 have? Well, we know how to do that. We start with 2 times x minus 5 equals 3. We follow SADMAP. We undo subtraction first on each side. That leaves me with 2 times x equals 8. And I bet you could even solve this one pretty quickly. I mean, we would divide by 2, and I'll just move to the right here. But that's just going to give us, of course, x equals 4. Okay, so the solution and the only solution to this is x equals 4. There's only one solution. How do I know it's the solution? Well, we can check it, right? And we go through and we replace the x with what we found the answer as, which is 4. And then we just check it out. So we do 2 times 4, which is 8. And then simplifying, 8 minus 5 is 3. Is 3 equal to 3? Yeah, check. X equals 4 is the solution. Now that's all review. So let's go ahead and look at C. C says we want to test 5 possible solutions, so 5 x values in this inequality. And remember, we read this inequality 2x minus 5, not alligator mouth. This isn't even a number, right? That's an expression. 2x minus 5 is greater than or equal to 3. Now, our job is to pick 5 different values for x and see what happens. So on your own, or by listening to me if you like, let's just pick 5 of them, right? And I'm just going to set them all up right now. So there's 1, here's 2, 3, 4, and 5. And if I had enough time, we would go through and you guys would share out which values of x you wanted to use. But I don't know. Let's just pick a few of them. Let's just try, I don't know, how about 5, 4, 3, 2, 1. That sounds good. Some other students in the past have picked negatives, they picked 0, they picked decimals. All those look great. But let's simplify these. Now, we'll have to do some mental math here, but I have faith in you guys. There is multiplication and there's subtraction. And in simplifying, this is PEMDAS, we do multiplication ahead of subtraction. So we're going to start with 2 times 5, which is, hopefully you all said 10, 10, and 10 minus 5 is 5. So this becomes 5 is greater than or equal to 3. Is 5 equal to 3? No. But is 5 greater than 3? Yes. So that means that the x value I used, x equals 5, is a solution. And I'll just put a smiley face because it made the result true, 5 greater than 3. Okay, let's try our next one. We have 2 times 4, which is 8. 8 minus 5 is 3. So I end up with 3 is greater than or equal to 3. Is 3 greater than 3? No. But is 3 equal to 3? Yeah. So this is also a solution, x equals 4. Okay, let's try 3. Okay, if we try 3, 2 times 3 is 6. 6 minus 5 is positive 1. Is 1 greater than or equal to 3? Well, it's not greater. It's not equal to. So this one is not a solution. It didn't work for either the greater or the equal to, and so we're out of luck. 2 to go. 2 times 2 is 4. 4 minus 5, so we're at 4, we're subtracting 5. I think that gets us to negative 1 this time. Is negative 1 ever greater than a positive number? Well, certainly not. And so x equals 2 did not work. Let's try this last one. 2 times 1 is 2. 2 minus 5, I think that gets us to negative 3. Is negative 3 greater than positive 3? No, it's a negative. Is it equal to 3? No, negative 3 and positive 3 are two completely different numbers. And so x equals 1 is also not a solution. So when we tried these x values, we found 2 numbers that were solutions and 3 that weren't. So how many solutions do you think there are? Well, I found 2. But what if I tried something like 1,000? Can you do the mental math here? 2 times 1,000 minus 5. I'm pretty sure that's going to be bigger than 3. Same with 10,000. And so hopefully you're thinking that there are an infinite number of solutions. Because you're right. But unlike with equations, when there's an infinite number of solutions to this equation, that means every number works. We know here, though, that every number doesn't work. We saw 3 over here where they didn't work. An infinite number of solutions, but not every number. And so that presents a bit of an issue, where up above we had an equation where it was very easy to say 4 is the number that works. Yay. But now with this inequality, we have this weird situation where some numbers work and some numbers don't. So our struggle for at least the beginning of today is, how do we tell people which are the numbers that do work and which ones don't work? And so let's go ahead and solve this inequality. And my screen, of course, did its typical zoom back out. Let's solve this inequality using SADMAP. I mean, an inequality is pretty similar to an equal sign. I bet SADMAP's still going to work. So 2 times x minus 5 is greater than or equal to 3. I'll remind you of SADMAP over here. We have two numbers attached to x. The 2 is, of course, multiplying. We'll need division. And the 5 is subtracting. We'll need addition. So let's undo our subtraction first. I like to keep the inequality sign right there, and you really want to do that. A lot of students have a bad habit of turning it into an equals, but it's not an equals. It's a different type of sign separating both sides. So keep the inequality sign there. Negative 5 plus 5 cancels. 2 times x is greater than or equal to 3 plus 5 is 8. Last but not least, we undo the multiplying by 2 by dividing. And I ran out of room, so I'll just move to the right. Keep the inequality sign. 8 divided by 2 is 4. Now, it shouldn't surprise you too much that we got 4, because we got 4 up above, and it's pretty much the same equation. But when x is isolated on part E, what does that number 4 now tell you? It doesn't tell us there's only one answer that's 4. How do we read this? Well, we read this as x can be any number that's what? That is equal to 4, or, and that's this top part, right? Not just equal, but or greater than 4. So, for example, what's a number that's greater than 4? Well, hopefully you said 5. And 5 is what we tried up here. 5 made our equation true. What are other numbers greater than 4? 6, 7, 1,000, 1,000,000. All of those, based on our answer, should be values that make this inequality true. So why does 2x minus 5 equal 3 only have one solution, but 2x minus 5 greater than or equal to 3 have an infinite number? Well, it comes down to the greater than sign. This equal to means one solution, at least for now, versus this greater than is going to mean an infinite number. Now, there are two ways that we can tell people the exact number of solutions. One way is an algebraic way, right? And that's what we saw on E up here. We solved using algebra, and we found an algebraic answer that shows or tells people that x's can be any numbers that are 4 or larger. But another way we can show these solutions is graphically. We can graph all the solutions. So the first thing we need to know is that a solution is always graphed as a point like this. It's a closed circle. So let's graph a couple solutions. Just by doing what we did up above, we know that 4 is a solution. We saw that one work way up here. We also know that 5 is a solution. How do we show things that aren't solutions? Well, we actually use open circles. So we saw that 3, 2, and 1 were not solutions, so we can do open circles. So this open circle means not a solution. Now, there are other solutions besides 4 and 5. X greater than or equal to 4 means numbers 4 and larger. So 4 or 5, we could do 6, we could do 7, but what about decimals? 4.5 is larger than 4. So is 5.1, 7.2. I think there's a lot of numbers larger than 4. And although you could take some time and put in as many dots as you'd like, math has a very clever shortcut that will be the same as showing lots of dots. And that, of course, is a line. The definition of a line is it's a set of infinite numbers of points. And so what I'm going to do is I'm just going to start at 4, and I'm going to go to the right. And then at the end, I'll put a nice big arrow to show that all the solutions are the shaded part of the line. A shaded part of a line is just a collection of points. Sometimes in middle school, you also learn to just go up from the starting point and then to the right, and that works great as well. If that's cleaner for you, feel free to use it, right? The answer, this 4, is the starting point, and then we shade it to the right because those are the solutions. We don't do anything with the open circles. I was just showing you how you could show something's not a solution. So let's go ahead and flip to that next page and we'll try our second example. Our second example is the inequality x minus 4 is greater than 2. And the first one says find an x value which makes the inequality true. Well, let's pick something big. Let's pick something like x equals 10. Why not? X equals 10. Well, we're going to replace the x in our inequality, that's what we're taking over here, with 10. We keep the greater than sign, we keep the 2, and what is 10 minus 4? Well, that's 6. Is 6 greater than 2? Yeah, it definitely is, right? So I'll put a smiley face, so that means that 10 is a solution because it made a true statement. Great. Now, over here, they asked us about other solutions. They said, is 6 a solution? What about 6.1, 6.01, all these numbers? Well, let's just try the first one here. Is 6 a solution? We'll test it the same way that we did for 10. 1, 2, 3, 4. I'm going to split this into kind of like 4 little columns here. Since they gave us 4 numbers they wanted us to test. So we have 1, 2, 3, 4. And so I'll start with x equals 6. We're using the same equation. X minus 4 is greater than 2. So blank minus 4 is greater than 2. We'll try 6 in there. And what is 6 minus 4? Well, that's 2. And keep the greater than 2. Is 2 greater than 2? Well, no, it's not. That's false. 2 is equal to 2, but there's no equal to sign there. So is x equals 6 a solution? No, it's not. So let's go bigger than 6. Let's try 6.1 this time. That's just slightly bigger than 6. So I have 6.1 minus 4 greater than 2. I think that's going to be 2.1 greater than 2. Is 2.1 larger than 2? Yes, it is. That's true. So that is a solution. So 6 wasn't, but 6.1 was. So let's try a number in between 6 and 6.1. Think of 6.1 as like $6.10. Well, what's in between? How about $6.01? So 6.01. Okay? Same idea as before. 6.01 minus 4. We're trying to see if that's greater than 2. That'll be 2.01. And that is greater than 2. So that's good. Can we get even closer? Well, sure. 6.001 is going to give us 2.001, which is greater than 2. Can we get closer? Sure. And in fact, many of you are starting to think, can't we just add more zeros? Can't we just do 6.000 and then like an infinite number of zeros? How do we even write that with a 1 at the end? And you're right. When it says what's the smallest solution for x, it would be 6 with an infinite number of zeros and a 1 at the end. However, there might be an easier way than saying that since we don't really have a nice way to write that. And so that's what we're going to look at for the rest of this problem. How do we show someone what all the answers for x are, including the smallest answer for x? 6 doesn't work, so what's just bigger than 6? And I think we're actually going to answer that on C right here. Let's solve this using SADMAP. That one's not bad, right? There's only one number attached to x. We're going to add 4 to each side, keeping the inequality in the middle. And that'll leave us with x is greater than 2 plus 4, 6. All right. Now, imagine you're asked to solve x minus 4 is greater than or equal to 2. Let's do that one really quickly. Greater than or equal to 2. Isn't solving it the same? We add 4, greater than or equal, add 4. And that leaves us with x is greater than or equal to 6. So are these answers the same? No, I don't think so. I think these are certainly different, but they are very close. Okay? This answer on D says we can use every number greater than 6 and exactly 6. But the answer on C says you can only use numbers greater than 6, but you can't use 6. Isn't that what B's saying up here? So maybe instead of saying that the smallest number is 6 with an infinite number of zeros and then a 1, what if we just said it's any number bigger than 6, right? 6 with an infinite number of zeros is bigger than 6. 6.001 is bigger than 6. And that's a really nice way. Instead of saying what the smallest is, instead of saying what it's equal to, we just say it's bigger than 6. It's a pretty eloquent way to do that. Now, how do we actually graph this? Well, we start with our number 6. That's going to be the center of our number line, right? There's our center over here. And we always start with a circle around the center. I like to put an open circle first because we can fill it in later. And then we'll talk about closing it up in a second. Then I like to go through and think, what are some possible solutions? What are values that are greater than 6? Well, 7 is larger, and 8, and 9, and 10. And then we saw up above that 6.01 and 001 and everything like that looks good as well. So I think what we can do here is we can connect from 6 all the way over to the right. But what do we actually do at 6? Well, could we use 6? Was 6 a solution? No, it wasn't. And so what we're going to do is we're actually going to leave an open circle around 6. We talked on the other page. An open circle means it's not a solution. And I really like to think of an open circle as kind of like a force field. It's around 6. We can't use 6, but it does tell us kind of where we're starting. It says 6 is our starting point. We can't use it, but we can use anything to the right because those are the numbers that are greater than 6. And so here's our quick conclusion. Oftentimes, you're going to be asked to graph the solutions for inequalities. To do this, you draw a number line. It's not always going to be given to you. I like you to center your number line around the solution. So 6 is in the center, not 0. 6 is in the center. And then if your solution uses greater than or equal to or less than or equal to, you use a closed or solid circle on your number line. But as we saw up above, if you see a greater than or less than without the equals to, you use an open or an empty circle on your number line. So really there's only kind of two main differences with inequalities. You still use SADMAP to solve them. It's nothing too crazy. But oftentimes you're going to be asked to graph the solutions. And with graphing, we need to know the difference between open and closed circles. There's kind of one other difference, and all of this is really the same difference, but maybe phrased in a couple ways. The second difference really comes down to how you write your answer. So let's look at a quick example. X equals 3 and 3 equals x. Do those mean the same thing? Well, yeah, that's true, right? X equals 3 is the same as 3 equals x. Whether you read it forwards or backwards, it's still just telling you the value of x is 3. But is that true for inequalities? So if I see x is less than 3, and we compare it to 3 is less than x, is that the same? And I think one way to think about this then is just to replace x in the red equation, the red inequality, with a value that's true. So what's a number that's less than 3? 0. Sure, let's try 0. So 0 is less than 3. That's true, isn't it? But what if we did the same thing on the other side? We have a 3, we have a less than, and then we put in a 0. Is 3 less than 0? Or think back to your alligator mouth. Is the alligator mouth eating the larger number now that they're both numbers? No, it's certainly not. 3 is not less than 0. That's false. So do they mean the same thing? No, that's false because when we tried a number that worked in one, if it was the same, it should have worked in both. So what is the same as x less than 3, right? If we had x less than 3 and we're like, we want to rewrite this, rewrite. And I wanted to put the 3 on this side and the x on the other side, you might, and many students do this, think, oh, it's a less than sign. We'll just keep a less than sign. But we just saw over here we can't do that. That doesn't work. So I'm going to cross that out. So what's the right way to do it? Well, you can think like your alligator mouth that you learned in middle school. You can switch the 3 and the x, that's fine, but think about where you started. That alligator mouth, we'll make it green for our alligator, is trying to eat the 3. If you switch the sides, what does the alligator mouth still have to be doing? It still has to be eating the 3. And so, x less than 3 is the same as 3 is greater than x. If you switch the sides, you need to switch the direction of the inequality sign. And that is weird. But we're going to practice that a whole bunch of times. So jumping on to our next page, we have a couple practice problems. Now, what we just talked about a little more formally is that the symmetric, think symmetry. If you have something with symmetry, you can fold it. It's the same on both sides. The symmetric property of equality tells us that if A equals B, then B equals A. Right? But it's trickier to use with inequalities because inequality signs are directional. Less than versus greater than means something different depending on which way the inequality sign is pointing. So let's go ahead and try a couple of these down below. It's going to ask you on A, B, C, and D to go through and first explain in words what they mean. So for example, in A, in words, this means 4 is less than x, THAN, when you're comparing. Then they're going to ask us to switch the order just for practice. So we're going to put the x first and the 4 second. The mouth currently is trying to eat the x. So when you switch the sides, what does the mouth still have to be trying to eat? Oh, that's right, the x. So 4 is less than x is actually the same as x is greater than 4. They mean the same thing. You can even read it backwards. X is greater than 4. So how do we graph that? Well, we take the 4, we put it in the center of our number line, and then I always ask that you guys give at least 2 more numbers on each side of that. The positive numbers moving to the right, like 5 and 6. The negative numbers moving to the left, like 3 and 2. So I always want a couple numbers above, a couple numbers below. How do we graph this? We start with an open circle. We can always fill it in later. And then we ask ourselves, 4 is less than x. If that's confusing, let's think about x is greater than 4. What are numbers that are greater than 4? Well, certainly 5 is greater than 4. 6 is greater than 4. 5.5, 4.5. Now that we've seen a few numbers to the right of 4, our solutions, that tells us we need to shade to the right. Last but not least, do we fill in the circle? No, this is open because there is no equals, right? Up above, there's no equal sign. And that's that. That's about as hard as today gets. So if you have the time, why don't you go ahead and pause me and try B, C, and D. But if you don't have the time, you can definitely just keep listening and I'll keep doing the problems for you. Okay, B has the x already on the left side, and then we have the greater than or equal to sign. We need to be able to read those. So how do we write this? It says x is greater than or equal to -1. Let's rewrite it. Good practice. So -1 on the left side, x on the right side. The mouth is trying to eat the x here. So let's make sure when we rewrite it, the mouth is still trying to eat the x. This says -1 has to be less than or equal to whatever x is. And they mean the same thing if you think about it. How do we graph? The -1 goes in the middle. We put a few numbers that are more positive than -1, like 0 and 1, and a few numbers that are more negative, like -2 and -3. We start with an open circle at -1, and then we ask ourselves, what numbers are solutions? X is greater than or equal to -1, so what are numbers that are greater than -1? Well, those are positive numbers like 0, 1, 0.5, -0.5. Now that we have a few solutions, we can go through and shade to the right. And I'm just showing the other way you can shade, right? You could shade on the number line or above. Last but not least, do we fill in the circle? Yes, we do fill this in because, so I'm going to say closed, because there's an equal sign. Do you guys see the equal sign in the problem right here? And that's that. 2 to go. Okay. 5 is greater than or equal to x. Let's flip it around. X on the left, 5 on the right. Notice that the mouth is trying to eat the 5, so let's keep it going that way. And so another way to say that 5 is greater than any x value is that the x values have to be less than or equal to 5. So here's our 5. Positive numbers, negative numbers. Numbers larger than 5 to the right, smaller than 5 to the left. Start with a circle, and then think about solutions. I like to read the solutions when the x is on the left, but it's up to you. X's that are less than 5, what are numbers that are less than 5? Well, 4, 3, those are numbers to the left. Now, you might remember from middle school that maybe your teacher taught you that whichever way the inequality sign is pointing is how you shade, right? If you look at this, this inequality sign is pointing to the right, or I'm sorry, to the left, so you shade left. But that's not a really good way to think about it, because if you look up here, this inequality sign is pointing to the right. So I'd be careful about using that rule. You can make it work, but I'm not going to tell you how. If you want to figure it out, go for it. Okay, last but not least, is this an open or a closed circle? Well, there's an equal to. That means it is closed. 5 is allowed to be a solution. 1 to go. -3, I should probably write this. -3 is greater than x. Let's flip it around. X, -3. Mouth is trying to eat the -3. So this is the same as saying x has to be less than -3. -3 in the middle, positives, negatives. -2, -1, 0. And more negatives are -4 and -5. Start at -3. Think x's are numbers less than -3. Which way is less than? Towards the positives or the negatives? Well, negatives are always smaller, so we want to go this way. So solutions could be -4 or -5, which means we're shading to the left. And do we fill in the -3? No, we can't use it. -3, it would be equal, and there's no equal to sign. All right, the very last part of this before we get to our summary and some practice problems there's one last strange issue with inequalities. With equations, as long as you do the same thing, the same operation to each side, the equation stays equal. Let's just double check to make sure that's true with inequalities. Currently, 5 is less than 20. That's very true. Let's go ahead and multiply both sides by 2. And see if that stays the same. So times 2, right, up here, times 2. And that gives me 10 is less than 40. Is that true? Is 10 smaller than 40? Yeah. So it seems like if you multiply both sides by the same number, nothing changes. Okay, let's try one more just to be sure. We'll do the same thing, but now we'll multiply by -2. There we go. Okay, 5 times -2, that's -10. And this one's -40. Is that true? Think about a number line, right? Here's our positives, here's our negatives, here's 0, here's -10, here's -40. Is -10 smaller or less than -40? Well, that's not true. -10 would have to be over there. that ends up being false. How would we change this to make it true? Well, to change it, we would say negative 10 is greater than negative 40. That's true. So that's kind of weird. When we multiplied by a positive, the end result was true. But if I multiplied by a negative, we got it false. We had to switch the direction of the inequality sign for it to be a true statement. As we've seen before, multiplication and division are kind of friends in algebra. Usually what is true for multiplication is true for division. So let's try this here. We have 5 less than 20, and they want us to divide both sides by 5 using that fraction for division. Now when I divided by 2 or multiplied by 2, we stayed true. If I divide by 5, I would expect this to be true as well. 1 and 4. Is 1 less than 4? Yeah, that is true. Okay, now there was an issue when I multiplied, but not by positive. The issue only came up when we multiplied by negatives. So let's try this over here. Let's do the same thing again, but now let's divide by negative 5, like so. A positive by a negative is a negative 1. Positive by negative 5 is negative 4. Is negative 1 smaller than negative 4? So if 0 is over here with the positives, we have negative 1, negative 2, negative 3. Here's negative 4. And I wrote a 3. Awkward. Is negative 1 more negative than negative 4? No, that's false. So what do I have to do here to make this a true statement? I have to change the direction of the inequality sign. Negative 1 is greater than negative 4. And so we can see this issue cropping up with both multiplication and division, but not all multiplication and division, just multiplication and division with negative numbers. So let's summarize this and then try to actually use it. When you add or subtract on both sides of an inequality, you don't need to do anything to the inequality symbol, just keep it facing the same direction. When both sides are multiplied or divided by a positive number, keep the inequality symbol facing the same direction. The issue that comes up, though, is if you multiply or divide by a negative number, your answer is going to be false. You have to switch or reverse the direction that the inequality sign faces for your answer to be true. Okay, so let's try some. On this last page, I have 9 problems, which might seem intimidating, but almost all of these 9 problems are 1 or at the most 2-step equations. So what I'm actually going to do is I'm going to go through and solve each of these equations first, and then we'll go back through and do the graphs. Okay? Now just be careful, because if you multiply or divide by a negative, you do need to flip the sign of your inequality. So let's see how that works. Here's A. X plus 1 is less than 7. Only one number attached to x, it's the 1 it's adding. How do we undo addition? Well, we subtract. Subtract 1 from one side, subtract 1 from the other. These cancel, and let's see, 7 minus 1 is 6. And we're done. X less than 6 will be a solution to the equation. Like I said, this isn't bad, guys. Let's try another one. X minus 15 is less than 20. Well, we can just add 15 to one side, add 15 to the other. 20 plus 15, that's 35. X is less than 35. We're cruising. 2 problems done out of the 9. Ooh, our third problem, though, throws a wrench in our plans because now there are 2 numbers attached to x. There's a 3, which is adding, and of course a 2, which is multiplying. Luckily, we know SADMAP, though, and it tells us to undo addition first. I don't know why it's still blue, but that's okay. So that leaves me with 2 times x is less than or equal to 12, going back over this. And we'll finish off the 2 that's out front. Divide by 2. And it leaves me with x is less than or equal to 6. Still nothing crazy. 3 problems done in the space of maybe 3 minutes. Okay, let's try a couple more. Here comes D Maybe, if my screen will cooperate. D is a little bit weird because I don't see a number in front of x, but at this point in our algebra careers, we know what number is hiding there if there's a 1. And we also know to not fall into the trap, the 1 is not subtracting. What's connecting the 1 to the x is multiplication. So to undo multiplication, we divide like so. There we go. These cancel, and we get x is greater than -2. Hopefully you felt the awkwardness in that silence because there's something we missed here. Let's go back to the beginning. It says, if you multiply or divide by a negative, change the direction the inequality sign faces. Oh my gosh, I might have forgotten about that all the way through. Well, in the first problem, I subtracted. That's not multiplication or division. Second problem, I added. Nothing, no issue there. Uh-oh, third problem, I divided. Did I need to change it? No, I divided by a positive, and as we saw on the previous page, that still keeps the answer true. But D is where the issue comes in. We divided by a negative. So you might want to make a note. Divided by a negative. So switch the greater than. So this is not our answer. Instead, it should be x is less than -2. We had to switch this sign that was in the middle when we divided by a negative. Otherwise, our answer will not work. The values we get won't work in the original equation. Okay, let's look at E. A little more complicated, this 10 minus x. I've mentioned several times in my videos that I like to write the x first. So this is a positive 10, that's a negative x. Let's switch the order. Negative x, positive 10. Right. Oh, and that same issue as before. Let's put the invisible 1 in front of the x with multiplication. Okay, thinking back to SADMAP, I now see that there are two numbers attached to x. There's a -1, which is multiplying, and there's a 10, which is, of course, adding. What do we undo first? Well, the 10. So let's subtract 10 from each side. And this is -1 times x is greater than, let's say, 2 minus 10. That's -8. Last but not least, let's divide off the -1. And I bet I didn't trick you this time, because we're dividing by a negative. A negative divided by a negative is a positive, but that's not the important part. We divided by a negative, we better switch that sign so it becomes a less than sign. Now that we're in the groove, we can move faster. Oh, we saw something like this before, didn't we? -1 times x greater than or equal to 2. Divide off the -1. We're left with x. Positive by a negative is a negative. And we divided by a negative, so flip the sign. Keep the equal to still, though. 3 to go. G says not x over 3. We don't read that fraction as over anymore. Instead, we read that fraction as divided by. And my screen is struggling, but I'm sure we're going to get back there soon. There we go. So I have x divided by 3 is less than 2. How do we undo division? Well, we multiply. Now, wait. So when we do that, 2 times 3 is 6. Since we multiplied, should we change the sign? Nope. Only if you multiply by a negative. So x is less than 6 is perfect. But here seems to be our negative. Now notice this h1 says x divided by 3 with a negative out front. Well, what I really like to do, and this is what we're going to practice a lot next unit, is we're going to take this negative and move it to one of the two numbers. Now, since x isn't actually a number, I'm going to move the negative down to the 3. These mean the exact same thing, but I think this gives us a clearer idea of what we need to do to isolate x. X is being divided by -3, so I'm going to multiply by -3. Multiplying and dividing cancels, leaves us with an x. 2 times -3 is -6. Do I need to change the sign? Yeah, we multiplied by a negative, so the sign needs to flip. Last one. 3 minus x divided by 4. Nah, I don't like the order. I'm switching it. It's a positive 3, and I'm going to move the negative onto the 4. So x divided by negative 4, positive 3, greater than 2. There's two numbers attached to x, though, so we do need to remember our SADMAP process. We know that the 3 is adding, and the negative 4 is dividing. Reading through SADMAP, we undo addition first. So let's subtract our 3 from each side. Leaves me with x divided by negative 4 is greater than, let's see, 2 minus 3 is negative 1. Last but not least, we undo division with multiplication. These guys cancel. It leaves me with x. Negative 1 times negative 4 is positive 4. And since I ended with a positive, I don't need to flip the sign, do I? Oh, yep, you do. We multiplied by a negative, and that's enough to make us flip the sign. Multiply or divide both sides by a negative, you gotta flip. All right, at this point, let's start going through the number lines. And I think the first thing I'll do is just get the numbers in the middle and decide if they're open or closed circles. And since I'm already at the end, let's just start here and work backwards. 4, we'll put a couple more numbers, 5, 6, 3, 2, open circle. And then we think, do we need to shade it in? No, there's no equals to up above. So we're pretty much done with that one. Let's look at this guy. Here's negative 6, negatives, positives, negative 7, negative 8, negative 5, negative 4, open circle. Do I shade it in? No, there's no equal to. Next one, 6, couple larger, 7, 8, a few smaller, open circle. Do we shade it in? No, there's no equal to. So let's jump up. Negative 2. Here's negative 3, negative 4, negative 1, and 0. Open circle. Do we shade it in? Nope. Moving on. Now, again, I'm not finishing these number lines. We're going to come back to these in a second. But I'm just kind of getting that same starting point for each of them. 8, 9, 10. 7, 6. Open circle. No equals to, so keep it open. Negative 2, here's negative 3 and negative 4. Negative 1 and 0 again. Open circle, do I fill it in? Yeah, there's an equals up there. And if there's an equals, then we need that closed or filled in circle. Okay, looking up here, we have 6. Let's do a couple numbers larger than 6 and a couple smaller. Open circle at 6. Oh, but there's an equals. We need a closed circle at 6. 35 seems intimidating, but it's just a number. 36 and 37. A few smaller. 34, 33. Open circle. Don't shade it in. There's no equals. And 6. 6, 7, 8. 5, 4. Open circle. Don't shade it in. Okay, last but not least, we need to figure out which way to shade. So, right, we need to actually shade the number line outside the circle. This says we want x's less than 6. So what are x's less than 6? Well, that's why I asked you to put two numbers. There are two numbers on here that are less than 6. 5 and 4 are less than 6. And so we go through and shade those in. Okay, what are numbers less than 35? Those are numbers like 34 and 33. So we shade to the left. Less than or equal to 6? Well, we already took care of the equals. What are numbers less than 6? 5 and 4. Okay, moving on through. Less than or equal to negative 2? Well, less than negative 2 means more negative. That's like negative 3 and negative 4. Less than 8? We get the idea. Less than's moving this way. In fact, a lot of these are less than, aren't they? Less than negative 2. Less than is to the left. Okay, less than 6. Are they all less thans? That's hilarious. They are all less thans going all the way through. Maybe we will update this for next year and make them not all less than. But that's okay. They are all less thans, all to the left, and we're set. That was pretty fast, I think, to finish these 9 problems on the back. So, to recap, there are a few things we needed to go over. If you multiply or divide both sides by a negative, what do? Flip the sign. If you want to rewrite an inequality, you totally can. Just make sure you look and see where the alligator mouth is facing and keep it facing towards that same letter or number. Eating the x, still eating the x. Beyond that, if we graph, we use closed circles if there's equals to, open circles if they're not equal to, and we shade the solutions that work. So hopefully this is a nice intro to inequalities. We'll do some advanced inequalities over the next couple of classes, but this is the nice foundation. So if there's anything that didn't make sense, please feel free to ask. Always happy to help. And I wish you the best of luck on your independent practice and your knowledge check next class.